Well, first, thank you very much, Mr. Pankaj. Very glad to be here, glad to be able to speak with you all at CII. Um, Grateful for the presentation that we just heard. It was definitely very enlightening. But as you just expressed, I want to talk a little bit about our experiences in synergizing multiple solution approaches. Um, First, I'll provide just a little bit of background about myself. I received my doctorate degree just recently, a little over a year ago from the University of Utah. I'm in the Department of Chemical Engineering. My doctorate work was focused on one of the aspects of reality that you expressed is permeating the electrical industry, and that's this variable load. Give me just a second, I'll bring up this pointer. All my work was focused on what do we do with these power plants when they're ramping up and down minimum load to maximum load multiple times a day. This is something very common to the work that I focused on, and primarily how do we use artificial intelligence to help our power plants to be the most efficient and also emit the fewest amount of emissions while operating in this manner to enable renewable energy and the other reasons, the other factors that contribute to load following. Um, And so that's with that as my background. I've had a fair amount of experience in this work, and talk. What I want to do now is talk with you all about um, what we've been able to do since my doctorate work and at various sites across the United States and internationally. So some very quick introduction and background. I don't have to tell all of you, I'm sure, how complex power generation is. Um, Not only is there a boiler and a massive fireball that we have to somehow control to generate energy to then send to a turbine, we have to manage soot throughout the system. We have to take care of the temperature of the steam within the system itself, using steam temperators as well as other factors, other parameters in the system. Besides that, we have to manage the air that's being introduced to the system and removed from the system via flue gas. Then we have to do something with the fly ash and different emissions such as SO2, the particulate matter, all these other things that are going on. Then aside from what's going on in the actual combustion process and downstream of that, we have to do things with our fuel. So we have to take care of our pulverizers. We have to somehow properly manage the characteristics of the fuel that we're operating with. And that's something that is very difficult to do because, as you're all aware, it's constantly changing. Besides that, we have aspects like the drum, and then we have to actually control the turbine, which is, at the end of the day, what's actually producing power. And then we have ancillary systems around the turbines, such as the condensers and cooling towers. There's just so much going on in these power plants that it's, the first question is, how do we control? How do we actually manage integrating all these systems? And that is the role of the DCS. The definition of the DCS is a distributed control system. And the point of that is that it distributes control of individual components, such as those I just talked about, to enhance reliability and robustness of the control system, so that each component focuses on a single piece, essentially, and it's able to be more reliable, focusing on those individual pieces, and then they communicate upwards, basically through these different levels of control to realize overall management of the process. So if we go back and look at our power system, though, and now we want to start discussing optimization, well, that opens up a whole other list of competing and contradictory factors that we have to account for and somehow properly manage. We have the combustion itself, where there's air and fuel. We have to try to somehow have maximum combustion efficiency while also managing temperatures. There's again ash buildup that affects heat rate and other tube metal life, degradation of the unit. There's actual temperature control using the temperators again, and aspects of combustion. We have things that we can do to optimize air management within the system. Other things on the back end of the process, emission rates, ash management for LOI and byproducts for selling that. There's things we can do also for the fuel. There's just so many different contradictory objectives that can go on inside of these systems that how do we actually optimize? How do we realize enhanced control of these processes in a way that synergizes across the system so that the entire process is overall better? And so that's really the question of the day. One of the things that's what I'm going to focus mostly on throughout the remainder of this presentation is how do we do that? And what we've introduced, what we like to phrase this as, is a new control layer within the DCS model. We call this the add-a-variant control layer. Essentially, add-a-variant means to assist, and it's an assistant to operators and to the DCS itself to enable both to maximize their own potential, while it itself is a flexible, agile component that utilizes data and artificial intelligence with the right methodology applied at the right components and the right levels across that large distributed process, so that everything can communicate with one another and it gains an overall better picture and understanding of the system. A couple of key differences between the DCS and add-a-variant control that I want to point out very quickly is that really overall the DCS's main focus is reliability and consistency. It's meant to realize the same level of control and the same procedures time and time again. It's repeatable so that we know exactly what to expect. That way it's safe and we can trust it. We don't have any issues or questions about what's going to happen in a given circumstance. That's the idea behind DCS control. But as we all know, every moment is not the same as the last, and that's where the role of add-a-variant control comes in, to be that flexible, agile component that uses understanding of previous operation and what are the current unit characteristics to adapt operation to what's happening instantaneously in this moment. And that's really the main differences, the key to why this add-a-variant control layer exists and why we try to operate there as a component above the DCS, interacting directly with the DCS so that it can fulfill its job of being safety critical, robust, repeatable control. And then add-a-variant control is what allows that synergistic optimization using advanced AI algorithms as well as other control methodologies. So how do we actually realize this add-a-variant control? Again, just real briefly, the idea of add-a-variant control is to be an assistant. It's really a bridge between operators and humans and machines so that they both can maximize their own potential. And a key component of it is that it's designed to implement the right tool for the right job, meaning that sometimes AI isn't the best solution. You know, it's very smart and it's an excellent component and tool, but there are processes and certain objectives that are better accomplished using other methodologies. And so add-a-variant control utilizes the broad database and list of various control methodologies so that the best is used for each individual objective. The way that we implement our add-a-variant control is through the Griffin AI toolkit. Inside of here, we can communicate directly with the DCS and the plant system-wide, develop control applications and logic for whatever objective it may be in whatever component, be it cooling towers or steam temperature control, combustion control, etc. And then there's the ability to develop advanced AI or more traditional regression or empirical models. And there's also some other tools to utilize additional artificial intelligence methodologies through evolutionary algorithms and optimization. And so I'm a very results driven and oriented person. So that's what I want to focus on primarily here and discuss with you what those results are. So we implement our system through a no-code development platform, meaning that it's very easy to interface with, very easy to interact and develop new control in response to, in the moment, recommendations from operators and engineers. There's a lot of AI components inside of here, such as neural networks, which are very capable of learning a process from operational data over time the system learns to very closely, if not nearly perfectly, represent a process, depending on the complexity of the process, of course. All this is done using immediately available data in real time. And then we use evolutionary algorithms and different methods of optimization so that we can identify the best operating conditions to realize whatever objective it may be. This essentially takes a million different guesses, this particle swarm optimization, at what optimality looks like, tests it, and then decides what truly is optimal to find the minimum, the global minimum of a process and in its current state. Everything that we do bases itself off the DCS curve so that it's reliable, it's robust, there's no hesitancy or worry about the process drifting into an unsafe or unreliable location. And it interacts directly with the DCS. There's an opportunity for operators to turn the AI optimization system on or off if it's active. Griffin optimizes a process, calculates what the best set point should be, determines the bias based off of the DCS's unbiased demand, and then sends that bias into the system, effectively realizing closed loop control using these biases. And one other key thing is that our system resides completely within the network of the DCS so that there's no outside communication, so that there's no worries about cybersecurity or other issues like that. Everything's inside of the DCS's own network, so there's no issues or concerns there. So now we've been able to apply these systems at a large number of different facilities and units, in total about 23 different units, 15 tangentially fired or corner fired units anywhere from 300 to 800 megawatts. Some 4-corner, some 8-corner units. Then we've also done a large number of wall-fired units as well, single wall and opposed wall fired units, similarly sized applications. Very quickly, just a brief history. Really, we've been doing this over the past 8 years. All of these are closed loop control, meaning that the operator simply turns the system on and it's optimizing from there on out. It's determining the optimal operational parameters, and without the operator having to do anything else, it's controlling the unit within a range of control around the DCS curves. As I mentioned, we've been doing this about 8 years at a multitude of different size boilers and different configurations, all with many different DCS systems. That's another important feature of this application, is that it's DCS agnostic. It can really interface with ABB or Foxborough or Emerson, any of these different vendors that exist out there. And then a short history as well of our wall-fired solutions. Some results here. First, we'll talk about a site where we've applied together work for emission rates, heat rates, temperature control, and system degradation. So first, emissions. What you see here is quarterly averages across the unit's load range of emission rate. When we began, this dark green line, towards the close of our project, this is over 2 years of the system self-learning, self-adapting itself as more operational data is achieved and collected. In total, about a 23% decrease across the entire unit's load range, from minimum load 25% of maximum capacity to 100% capacity. The other key thing here is the system had a service factor of over 85%, meaning that it's doing this nearly all the time. An example of an on-off test, the system was off over here on the left side of the graph for about 12 hours. Then when the Griffin system is activated, almost immediately within an hour, NOx is decreased by 15% for a similar load, with no real detrimental effect to other parameters such as CO. And we looked at a total of 6 months, 3 months of analysis on the left and on the right. About 8.5% decrease during this quarter, these 3 months, 12.5% decrease in NOx during these later 3 months here. And then another key thing that was possible here was the fact that the system was able to realize NOx emission rates that had never been realized before by operators or anybody else running the unit. The optimization system in Griffin system capable of finding new configurations to outperform anything that's been seen previously in the historical data. Now then, if we look at tube metal degradation inside of the system due to high metal temperatures, see that before intelligent control was initiated, we see over the time span of about a month, 257 instances of high tube metal temperatures above this solid black line here. After advanced control, a little bit more active parameter, control parameter down here in the purple, we see that over an 80% decrease in the number of instances of high tube metal temperatures, representing greater tube life inside of the unit. One other capability we've been able to do is identify tube leaks far earlier than able to do so traditionally. And we do this using advanced dimensionality reduction tools and process analysis. These signals here are what the plant looks like over 3 days. Very messy signals for these different load swings. What our tools do is they break this information apart into very easily identifiable regimes, recognizing that here this is normal operation. Here likely the tube had a pinhole leak, was starting to get close to erupting and failing. And in the red, you see it's an entirely different operating regime, meaning that these parameters indicate something's happened inside of the unit, which was a tube leak. So almost 12 hours before the unit actually identified the failure and come offline, able to know that there was a problem long before operations would have traditionally. Beyond that, at this same site, able to do cooling tower optimization in this application. The objective of reducing auxiliary power usage. See in this example, by adjusting the fan speeds of individual cells in this cooling tower, this is a forced draft cooling tower, it will reduce auxiliary power usage by over 5%. It's just a summary of those different advantages and results at this single site. And that's a key thing here, is that these are synergized optimization objectives. These are all working congruently in parallel with one another to see all of these benefits on a single system. That's the out-of-variant control benefit right there. Multiple gains across the process. Very quickly, I'll talk a little bit about heat rate as well. Able to see improvements in overall heat rate on average in the range of 0.4 to 0.7% through just combustion optimization. See as high as 3% in individual observations, but on average about that 0.4 to 0.7% range. In another project we've done, able to see similar results in actually minimizing heat rate itself across the load range. On average about 1 to 1.5% reduction in heat rate here through, again, simply combustion optimization. When you factor in components like soot blowing and cooling tower optimization, all those other features, that heat rate benefit increases. Another application that we've done is managing mercury emissions and also pack injection to control mercury emissions. What we were able to see is that pack has a detrimental effect on other portions of the process, particularly opacity measurements at the stack. Through advanced control, we're actually able to lower the pack injection rate, which is shown by this average, this brown line compared to this blue line, while seeing lower mercury emissions and lower on average opacity and decreasing opacity alarms by over 95%. All of this through that out-of-variant control, applying the right control methodology to the right process, really keying in on the knowledge of the process. One thing that we strive to always do is gather knowledge from operations and engineers and develop that directly into our systems. Finally, another key thing we've done is the ability to predict coal quality in real time using operational parameters. See that by doing this at a particular site using readily available boiler, scrubber, and feeder data, able to predict what the coal quality is like and able to improve our predictions of unit operation and emission rates by over 40%. So drastic improvement in predictability and understanding of the unit and what kind of coal is being burned and how that affects the entire process. So in conclusion, wrap up very quickly, DCS control is meant to be safety oriented. That's really what it's the best at. Doing advanced controls inside of there is usually time consuming and expensive. That's really where out of variant control shines. That's its main purpose, is that flexible, agile layer to do intelligent control. Machine learning and AI is important, but that's not the only solution approach. It's important to use the merits of the process itself and to determine how you implement that control. And the toolkit framework, such as the Griffin AI toolkit, is really the best way to do that. In our case studies we've discussed, we see multiple benefits across different portions and processes within the system itself, decreasing a bunch of different objectives that we had. And then finally, as you stack different operational objectives, moving from simply combustion optimization to including knowledge-based SIP blowing, intelligent SIP blowing, and then also when you add in optimization of cooling towers, fan usage, and other components across the system, you see that those savings increase dramatically. This chart has been generated using about $100 per ton, metric ton coal, US dollars, and a plant service factor of 95%. You can see as high as nearly $6 million saved through these very simple digital solutions applied to a system. So thank you all for your time. Yes.